When people talk about fine-tuning a large language model, they often mean very different things. Some mean changing the prompt. Others mean training the model. So let's start with a simple question. What does fine-tuning actually mean? A large language model is, at its core, a huge neural network trained to predict the next token. During pre-training, it learns this behavior from massive amounts of text. Fine-tuning means modifying the model so that it behaves differently from the base model, usually for a specific task, domain, or style. And there are many ways to do that, ranging from not touching the model at all to retraining millions or billions of parameters. The main approach for fine-tuning are prompting. With this technique, we steer the behavior at inference time with no learning. Let's show an example. We could provide the following prompt. Classify the sentiment of this sentence as positive or negative. Sentence: I love this product. Answer. The model normally will answer positive. The second approach is in-context learning examples in prompt. This approach provides a way for temporary learning. Examples. Classify the sentiment of the sentences below as positive or negative. Example 1, I love this product. Positive. Example 2, this movie was terrible. Negative. Example 3, the food was delicious. Positive. Now classify this sentence. The service was awful. Negative. By looking to other samples in prompt, the model will learn to answer. Third approach is RAG, Retrieval Augmented Generation. This is not exactly fine-tuning, but it consists in adding external knowledge to improve model capabilities. Also in this case, the model is unchanged. Let's now present prompt tuning. This is different with respect to simple prompting because we train a small set of embeddings that act like a learned prompt. Only these embeddings are updated, base model is frozen. This is true parameter-efficient fine-tuning. PEFT, LoRA, adapters. This approach consists in training few parameters and it is the best cost performance. Full fine-tuning train all parameters with maximum control but high cost. RLHF, Reinforcement Learning from Human Feedback. It is a fine-tuning technique where a model is trained to produce better outputs by optimizing for human preferences, instead of just matching labeled data. Similarly, RLAIF is a reinforcement learning from AI feedback. Most real-world fine-tuning today uses parameter-efficient methods. These include LoRA, QLoRA, adapters. Instead of training the whole model, we freeze the base model and train small additional layers. This approach is affordable, fast, reproducible, and scalable. For most use cases, this is the best trade-off. In this video, I'll show you how to do parameter-efficient fine-tuning with LoRA. LoRA, low-rank adaptation, fine-tunes an LLM by adding small, trainable low-rank matrices to existing weights, while keeping the original model frozen. Let's quickly explain the intuition behind this method. Imagine each weight matrix in a transformer as a large table. Instead of changing the table itself, LoRA says, let's learn a small correction and add it on top. This can be achieved by dividing the weight matrix in two smaller rank matrices. That correction is constrained to be low rank, meaning that it captures the most important directions of change. We use far fewer parameters. Let's now go to a practical example. We will fine-tune a small language model to give us precise answers. We can use a small model as Qwen 2-0.5b. Let's load the model with Transformers library. Bits and Bytes config allows you to load massive AI models on consumer hardware by compressing the model's weights from their original size down to just 4 bits. Let's now test the model on a question and observe the output. We need to build the prompt. In order to do that, we need to tokenize the input that is to convert to a numerical representation by using the model tokenizer before feeding the model. Once the output is produced, we need to decode it back to natural language. We can have a look to the output. We can observe how the model is not able to provide an exact answer. It mentions some business ideas, but it also mixed them with general explanations and ask an additional question. We will now fine-tune the model on Alpaca dataset, but let's first of all load it. Alpaca is a dataset of 52,000 instructions and demonstrations generated by OpenAI's Text DaVinci 003 engine. This instruction data can be used to conduct instruction tuning for language models and make the language model follow instruction better. Let's define an helper function to define the prompt. We can then tokenize the whole dataset. Let's now define the LoRA config params. We can define the rank dimension of the adapter matrix, the scaling factor, the layers that will be fine-tuned, the bias, and finally the task type. In this case, the task is a causal LM. These are models designed to predict the next token in a sequence based on the tokens that came before it, moving from left to right. We can observe how the number of trainable parameters is much smaller when using LoRA. We now need to define the parameters for training. Let's give a brief overview of each of them. Output dir, the output directory where to save the model. The per-device train batch size is number of samples processed at once on each GPU. The gradient accumulation steps provides the number of steps before updating weights. The learning rate is peak learning rate, how big each weight update is. The number train epochs is the number of training epochs for fine-tuning. FP16 tells us to use float 16 precision. Logging steps tells us after how many steps to log the metrics. Eval strategy and eval steps are needed if we use a validation set and use the type of validation and the number of steps to perform validation. It is important to avoid overfitting. Save strategy tells the strategy to follow to save the model. In this case, the number of steps will be considered. Save steps, the number of saved steps. Load best model at end. If true, we will load the best model at the end. Metric for best model is the metric to use to validate the best model. Warm-up ratio. During the very beginning of training, your model's gradients can be unstable. Warm-up starts the learning rate very low and gradually increases it to the maximum value. A ratio of 0.05 means that for the first 5% of your total training steps, the learning rate will ramp up linearly. LR scheduler type defines the shape of the learning curve. Weight decay is a regularization technique used to prevent overfitting. Report to controls where your training metrics, loss, accuracy, etc., are sent. None tells the library not to log to any external cloud service or local dashboard. We will also define a data collator for language modeling. It takes individual samples from your dataset and batches them together into a format the model can actually digest. Let's now define the trainer and run our training. The training process is going to take several minutes according to your local resources. On my side, I'm using a NVIDIA 5070 RTX with 8 GB of VRAM. I've already trained the model before the video. Let's now load the model from the last checkpoint and run against the prompt. We will need to load the model with PEFT model class and set it in the evaluation mode. Let's copy again the prompt and let's run it. We can observe how the answer of the model has changed. It is now able to provide some business ideas. The last point is truncated because we limited the output to 200 words. During the PEFT fine-tuning, we have used a very small LoRA decomposition. This means that the number of updated weights was low. From one side, this allowed us to fine-tune the model on a smaller device, but at the same time we cannot expect amazing results. Possible improvements could be to increase the matrix rank in order to increase the number of fine-tuned parameters. We have also limited the datasets to the first 5,000 samples, but we could increase the number of the samples considered. We have now reached the end of this video where we have learned what it means to fine-tune a LLM model and which are the possible techniques. We've also trained a small language model with parameters-efficient fine-tuning on a custom dataset. I hope you've enjoyed the video and see you soon in the next one.